Hi class, welcome to our second lesson on chapter 18. What we're doing in this lesson is we're finding roots, zeros, and factors. And just to let you know class, these are really all saying the exact same thing. We're talking about polynomial functions here. So an example of a polynomial function might look something like this. Okay, and so the roots, zeros, are the functions. They're all saying the exact same thing. It's where it crosses the x-axis. So this one has 3 roots, or 3 zeros, or 3 factors. It's the ones where they cross the x-axis. So that's what we're talking about in this lesson. Before we go on, look at this math joke. Isn't this great? If you get it by now? Anyone not get it? This is the same thing as I. The square root of a -1 is an I, right? Imaginary number. 2 cubed is 8. This sigma means sum, and our pi symbol, or in this case, our pi. I ate some pie, and it was delicious. I love stuff like that. Okay, the degree. It's the highest exponent of the polynomial that tells you how many zeros, factors, or roots that there are. So we've talked about this before. We could look, and instantaneously, we can say, bam, the degree is 3. So that means that it has 3 roots, zeros, or factors. I know that there are 3 answers for what x could be. In the same way, our degree is 5. So if the degree is 5, we know that there's going to be 5 solutions, or 5 roots, zeros, or factors. Okay? So that degree is a very quick and easy way of telling us how many answers that there are. Okay, so with these, some of them might be real, which means they cross the x-axis. However, some of them are imaginary. That's when you take the square root of a negative number, and then you get an I in them. So we know instantaneously, bam, 3 zeros, okay? So if we look at our graph now, one of them is real, okay? So that means that if there's a total of 3 and one of them are real, that means 2 must be imaginary, because there always has to be 3 zeros. If one of them is real, the other 2 are not real or imaginary. In the same way, looking at this one, there's 4 zeros, okay? There's 4 roots, okay? How many of them are real? Well, how many of them cross the x-axis? So here it crosses, here, and here. So there's 4 times that it crosses the x-axis, and there's 4 zeros. So that doesn't leave any room for negative, or for imaginary zeros, class. So on this one, there are no imaginary roots. Okay? That's how we kind of look at this. Now, Descartes, he was a mathematician that did a lot of work with this kind of stuff, and he came up with this theorem. Now it says let f of x be a polynomial, so we're talking about polynomial functions, and they have real coefficients and a non-zero constant. Okay? So he found out that with every polynomial, if it crosses the x-axis to the right, so these are the positive number of zeros, that green part is, he found out that it's equal to the number of sign changes in f of x, or it's less than that by an even integer. Okay? And then he also found out that the number of zeros to the left, or the number of negative zeros, so in that blue part, when you substitute a negative x into our polynomial function and then count the number of sign changes, it is equal to the number of sign changes in that. Now, I could imagine that you're kind of confused right now, and that's just kind of fine. We're going to define this a little bit more as we go on to our next examples. But bottom line, to find out the positive number of zeros, right here, count the sign changes. To find out how many negative real zeros there are, count the sign changes in a negative x. So looking at this one, let's start practicing this. We're going to count the number of sign changes in our function f of x, or in this case, it's going to be p of x. So looking at this, it's positive x to the 5th to a negative 6x to the 4th. There's a sign change. Now I go from negative to negative 3x cubed. No sign change. Negative to positive 7x squared. There's another sign change. Positive to negative, there's another sign change, and negative to positive, there's another sign change. So it changes signs. 1, 2, oh, sorry. 1, 2, 3, 4. It changes sign 4 different times. So there are 4 sign changes, which means there are 4 positive real zeros, or less than that by an even integer. So if you subtract an even integer, which is 2, there could be 4 positive zeros, 2 positive zeros, or subtract 2 again, 0. Once we get down to 0, we don't subtract anymore. Okay? So I know that there's gonna be a total number of 5 zeros. Okay? But I know that there's not gonna be 5 positive zeros. I know there's not gonna be 3 positive zeros. It's either gonna be this, this or this, either 4, 2, or 0. Okay, so that really helps us out in determining where does it cross the x-axis at. Okay, now looking at this one, this is important, class, so pay very close attention to this. To find the number of negative real zeros, instead of p of x, I'm going to put a negative x in for every time I saw an x in this function. So as I do this, I'm going to put a negative x in here. Same thing here, 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 here. Now I want you to notice something. Let's see here. I'm just going to write down what it was. Our actual function was p of x. This is what it was before we changed any of these signs. P of x was equal to x to the 5th, and then minus 6x to the 4th, minus 3x cubed, plus 7x squared, minus 8x, and then adding 1. So what happened when we do p of a negative x, every time I see an x, which is here, 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 I'm going to substitute in a negative x. And then here were the results that we got. Okay, this one, this one, this one, this one, this one, when I put in a negative x. So now we're going to ask ourselves, how many times did it change signs? So it went from negative to negative, negative to positive. There's one sign change. Positive to positive, positive to positive, positive to positive. So this one had one sign change. There are 1 sign changes on this one. So that means there is 1 negative real zero or less than that by an even integer. So if we subtract 2, well, once we get down to 0, we don't subtract anymore, class. So this one, we know for certain it's going to have 1 negative 0. Okay? So once we subtract, and once we get to 0 or less than that, we don't need to subtract anymore. Now I want you to notice something, and this is going to be very important, class. When we had x raised to the 5th, and then we put in a negative x, it turned to a negative x to the 5th. Now watch this. It started off with a negative x, negative 6x to the 4th, and when we put in a negative x right here, it stayed a negative 6x to the 4th, didn't it? This right here and this right here are the exact same thing. Watch what happened when we had x cubed. This was a negative 3x cubed, and now it's a positive 3x cubed. So the sign changed. Watch what happened here. A positive 7x squared, and we ended up with a positive 7x squared. A negative 8x, and then we change signs to a positive 8x. And then obviously the 1 stays the same. So class, here's the bottom line. Whenever you have an odd exponent, 5, 3, and x to the 1st, or 5, 3, 1, the signs are going to switch. It go in from positive to negative right here. Okay? It went from negative to positive right here. It went from negative to positive. So whenever you have an odd exponent, the sign is going to switch. Whenever you have an even exponent, x raised to the 4th, it stays the same sign. Negative, it stayed negative. This was positive, it stayed positive. Okay? And that's going to be able to work on every single one of them. So now we're going to dive more into that now on this next problem when we're going to do it all on our own. So we have h of x is equal to 4x cubed minus 6x squared plus 8x minus 5. How many zeros are there? Bam! Our degree tells us there's going to be 3 zeros. Now how many positive zeros are there? Or how many zeros are to the right of the y-axis? Well, it's equal to the number of sign changes. So let's see how many sign changes there are. Positive to negative, 1. Negative to positive, 2. Positive, negative, 3. This one has 3 sign changes. So if there are 3 sign changes, that must mean that there are 3 positive zeros or less than that by an even integer. So subtract 2, there's going to be either 3 or 1. That's how many positive zeros there's going to be. Now what we need to do, class, is we need to do h of a negative x, because we need to find out how many negative number of zeros there are. So h of a negative x is equal to 4 times a negative x cubed minus 6 times a negative x squared plus 8 times a negative x, and then subtract 5. Now class, like I said, whenever you have an odd exponent, okay, the sign is going to stay the same. The sign is going to change. So this positive 4x cubed turns to a negative 4x cubed. This negative 6x squared, when it's an even power, it stays the same sign. So it stays negative 6x squared. This positive 8x, because it's x raised to the first, it's an odd exponent, which means the sign is going to switch. It's going to switch to a negative 8x. And then obviously the negative 5 stays the same. And here's the reason why. What's a negative x times itself 3 times? A negative x times a negative x times a negative x is a negative x cubed. Multiply that by 4 is a negative x to the 4th. See? Sign switches. Negative x to the 4th. Now this was a negative 6x squared, and it stayed a negative 6x squared here. Let me explain why. Because a negative x squared, what's a negative x times a negative x? It's a positive x squared. And what's a positive x squared times a negative 6? It's a negative 6x squared. So the sign did not switch. And that's the reason for all of that. So now knowing that, how many sign changes do we have? Negative, 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 negative. Well, this one has 0 sign changes. So if there are 0 sign changes, that means there aren't going to be any negative real zeros. There isn't going to be any. So knowing that, I know there's going to be a total of 3. So total number of zeros, this column right here, is 3. So a lot of times I just kind of write 3 in here sometimes, just because I know that there's always going to be 3. And then as I fill in my chart, I can erase as I go if I want to as well. So if there's 3 zeros, the total number, 3 of them could be positive or 1 of them could be positive. So 3 of them could be positive or 1 of them could be positive. Now, there aren't any negative real zeros because I found that doing h of a negative x. So if there aren't any, I'm going to put 0 here and 0 here. So now, class, this right here is always going to add up to my total number. Because if there is 3 positive, 0 negative, and there's a total of 3, that doesn't leave any room for negative or for imaginary zeros. So there isn't going to be any imaginary zeros. So 3 plus 0 is this number 3 right here. In the same way, if there's 1 positive 0 and 0 negative real zeros, that means that there has to be 2 imaginary, because I have to add up to equal 3. So 2 plus 1 plus 0 plus 2 is my total number of 3. So now I didn't use any other of these rows, so all I have is just these first top 2 rows. Those are my possibilities. That's what we're going to be doing on these next 3 slides, class. So the basics are the same in each and every one of these problems. So how many zeros does this one have? It has 5. Okay. How many positive zeros does it have? Well, 1 sign change, 2 sign changes, 3, 4. So this one has 4 sign changes, which means that there's going to be 4 positive real zeros, or 2 positive real zeros, or 0 positive real zeros. The reason for that is there's 4 sign changes, and then less than that by an even integer. So you subtract 2 every time. Now we're going to do the exact same thing for p of a negative x. Now class, like I said, the odd exponents change the sign. So this positive x to the 5th turns to a negative x to the 5th. But the even exponents stay the same sign. So this is going to stay a negative 6x raised to the 4th. Here's an odd exponent, which means the sign is going to switch, so that's going to turn to a positive 3x cubed. Here we have a x squared, so whenever the degree is even, the sign is going to stay the same. So a positive 7x squared. This sign is going to switch because it's an odd exponent, so a positive 8x, and then we have a positive 1. So how many sign changes do we have? 1. Just 1 sign change. So that means there's going to be 1 negative real 0. So we're going to have a total of 5. I know that with these 5 zeros, 4 of them might be positive, If it's not 4, 2 of them could be positive. If it's not 2, 0 of them could be positive. With these 5 zeros, I know for certain that one of them is going to be negative. So if I have 4 positive real zeros and 1 negative real zero, that doesn't leave any room for imaginary zeros, so I'm going to have 0 imaginary zeros in that row. If I have 2 positive real zeros, and I know I'm going to have 1 negative real zero, that leaves room for 2 other imaginary zeros. And the last one, if I have 0 positive real zeros, and I know I'm going to have 1 negative real zero, that means I'm going to have 4 imaginary zeros. So like I said, class, all of these right here, they have to add up to equal the total number of possible zeros in each and every row. Okay, so these right here, this has to add up to 5. This has to add up to 5. This has to add up to 5. Okay, so that's how you can always check your work as you go. And then these last rows and columns we never had to use. Let's practice another one. So this one, there are 6 total zeros. So if I know that there's 6 total zeros, how many of them are positive? There's 1, 2, 3 sign changes. So if there are 3 sign changes, I know that I am going to have 3 or 1 positive real zeros. 3 or 1. So now let's do r of a negative x. R of a negative x. So I know that the odd powers are going to change the sign. The even powers are going to have the signs stay the same. Here's an even power, so the sign stays the same. Here's an even power, so the sign stays the same. Here's an even power, so the sign stays the same. And then our constant term is going to stay the same as well. So again, on this one, how many sign changes are there? 1, 2, 3. 3 sign changes, which means there's going to be 3 negative zeros, or less than that by an even integer, which is 1. So there could be 3 or 1 negative zeros as well. All right, let's fill out our chart. We know there's going to be 6 zeros. It tells us that by our degree. So if there is 6, 3 of them could be positive, or 1 of them could be positive. Now if there is 3 positive, one combination is that there could be 3 negative. Okay? If there is 1 positive right here, a combination could be 3 negative. If that was the case, then we would have 0 imaginary zeros, and we would have 2 imaginary zeros. Because once again, these rows have to add up to equal 6. Okay? That's not the only possibility, because I could have 1 negative real zero as well, paired up with both of these. So if I have, again, 3 positive real zeros, or 1 positive real zero, with that, if there's 3 positive, I could have 1 negative, which would give me a total of 2 imaginary. This should have been the number 2. If there is 1 positive real zero and 1 negative real zero, that would leave a total of 4 imaginary zeros. And this concludes filling out our chart for this one. Last one of this kind. We have q of x equals x to the 4th plus 5x cubed plus 2x squared minus 7x. Now class, on that one of our first slides, it says that this one has to be a constant. If it's not, factor out an x. So I can take out a GCF right here of x, and that would leave q of x equals x times the quantity x cubed plus 5x squared plus 2x minus 7. Now this is a constant term, which is what I need before I start this whole process. So what I know is I know that x equals 0, this one right here, is a root, or is a 0. So now there was 4, but I know this is a 0, so now there's going to be 3 left. So there's going to be 3 other zeros. Okay, so this is my new degree. There's 3 other zeros. So which ones are positive, which ones are negative? So now, class, I'm doing the same thing that I did on the last few slides with this right here. There's going to be one sign change. So how many positive zeros are there? Just one. Let's talk about the negative sign changes. So if I put a negative x in to that one right there, I would have q of a negative x equaling the odd exponents change the sign. So this is now a negative x cubed. The evens stay the same, so plus 5x squared. Odd changes to a negative 2x. And then I have my negative 7. So this one has 1, 2, 2 sign changes, I believe. So if there are if there are 2 sign changes, 1, 2, that means that there is 2 negative zeros or 0 negative real zeros. So with this, let's fill out our chart. There's going to be a total of 3, because remember that's our new degree. So 3. Now, we know that one of them is going to be positive. So we're going to have 1s here. So if one of them is positive, we might have 2 of them negative, or we might have 0 of them negative. And those are our only possibilities. So we're only going to use the first 2 rows of this one. So if there is 1 positive, and if there are 2 negative, with a total of 3, that means 0 imaginary. Or if there is 1 positive and 0 negative, that would leave room for 2 imaginary. And that's what we have for this one. So I know that these might be kind of confusing. Be sure to let me know if you have any questions on these problems when you get to class tomorrow. The last thing we're going to finish on here isn't too bad. It might sound kind of confusing. The Rational Zero Theorem just means that the rational zeros, which remember what rational means, numbers that can be written as a fraction, they will be p divided by q, where p is a factor of this term, and q is a factor of the first term, which is this right here. Okay, so it might sound kind of confusing right now, but just take a look at this one right now. If we look at the factors of p and the factors of q, they are right here and right here. So what are the factors of p? What are the factors of 4? Well, it's 1 times 4 and 2 times 2. So the factors are 1, 2, and 4. The factors of q, which is 3, are just 1 times 3. So with this, I know that there's going to be 4 zeros. If they are going to be rational, they're always going to be factors where p is divided by q. So take these numbers and divide it by 1. So if I do that, what is 1 divided by 1, 2 divided by 1, and 4 divided by 1? Well, just 1, 2, and 4. Now, class, what we always need here is we need both the positive and the negative signs. So all of these are going to have plus and minus signs. Plus and minus 1, plus and minus 2, plus and minus 4. In the same way, all of these here, those are all factors of p divided by this factor of q, which is 3. So place 1 over 3, 2 over 3, and 4 over 3. So then we would get plus and minus 1/3, plus and minus 2/3, and our last one is plus and minus 4/3. So if we were to ask the question, where are the zeros in this function? Well, there's an infinite number of numbers, and now it's down to this many, okay? There can't be any other rational zeros except for those ones listed right there. So now for this last problem, let's do the exact same thing. Factors of 4 are 1, 2, and 4. Factors of 18 are 1, 2, 3, 6, 9, and 18. So if we want to ask ourselves, what are the possible rational zeros, which are ones that can be written as a fraction, we're going to place all of these over 1. So obviously, 1 divided by 1, 2 divided by 1, 3 divided by 1, it's just these numbers right here. So it's plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6, plus and minus 9, plus and minus 18. Now we're going to put all of these numbers and we're going to divide it by 2. Okay, now if there's any repeats, we don't have to write it more than once. So let's put 1 over 2, and we would get plus and minus a half. Now let's put 2 over 2, so what's 2 divided by 2? It's 1. Well, we don't have to write it because 1 is already written right here. So now we're on to 3. So 3 divided by 2 is plus and minus 3 halves. Now we're on to 6 divided by 2. 6 divided by 2 is 3, and we already have 3 written down. It's right there, so we don't have to write it down again. 9 divided by 2 is 9 halves, plus and minus 9 halves. And then our last one, 18 divided by 2 is 18 halves. And 18 halves is the same thing as 9, and 9 is already written down right here. So we don't have to write down that one. Okay, last thing, we have to place all of these now over the last factor of q, which is this 4 right here. So 1 divided by 4 is plus and minus 1/4. Now we have 2 divided by 4, which 2 divided by 4 is 1/2. We already have 1/2, so we don't have to write it down again. 3 divided by 4 is plus and minus 3/4. 6 divided by 4, 6/4 is 3 halves. We already have 3 halves right here. No need to write it again. 9 divided by 4 is plus and minus 9/4. And then our last one is 18/4. And 18/4 is the same thing as 9 halves, and 9 halves is already written right here. So out of an infinite number of numbers, these ones are the only possibilities for rational zeros for this particular function. So now our worksheet is going to be on 18.2. Kind of a confusing lesson. Be sure to let me know if you have any questions when you get to class tomorrow.